Hi everyone, a warm welcome. Myself Bittu with the Academy of Science and Technology. In this video, I am going to start the fifth module. First topic in the fifth module is Laurent series. You already studied about two series expansions, which are Taylor series and Maclaurin series. Now I am going to introduce a new series, which is Laurent series. If Fz is analytic at a point A, then with the help of Taylor series, we can express Fz in the form of an infinite series containing positive powers of Z minus A. If Fz is not analytic at A, we can't use Taylor series. Instead, we can use a new kind of series called Laurent series, consisting of positive integer powers of Z minus A as well as negative integer powers of Z minus A. Laurent series is also used for classifying singularities. Laurent series of Fz converges in an annular region R1 less than mod Z minus A less than R2. Really, an annular region R1 less than mod Z minus A less than R2 is the region bounded by two concentric circles with the center A and radii R1 and R2. Here R1 is always less than R2. If Fz is analytic in an annular region R1 less than mod Z minus A less than R2, then Fz can be expressed as Fz equal to A0 plus A1 into Z minus A plus A2 into Z minus A the whole square plus etc. plus B1 by Z minus A plus B2 by Z minus A the whole square plus etc., which is known as the Laurent series expansion of Fz. Here Ai's and Bi's are constants. Sometimes certain coefficients may be absent. By looking into the series, Fz equal to A0 plus A1 into Z minus A plus A2 into Z minus A the whole square plus etc. plus B1 by Z minus A plus B2 by Z minus A the whole square plus etc. We can notice that it contains two infinite series. The first series is an infinite series containing positive powers of Z minus A, and the second series is an infinite series containing negative powers of Z minus A. The second series is also known as the singular part of the series. Now, I would like to introduce two important series which are very useful in the Laurent series expansion. They are 1 by 1 plus Z equal to 1 minus Z plus Z square minus ZQ plus etc. Again, 1 by 1 minus Z equal to 1 plus Z plus Z square plus ZQ plus Z raised to 4 plus etc. Also, you must notice that these two expansions are valid in the region mod Z less than 1. These two series are very useful while finding the Laurent series expansion of a given function. See here, you must also notice that in these two expansions, in the term 1 by 1 plus Z, in the denominator, the starting term is 1 and modulus of second term is less than 1. With this little introduction, let me start. Next, let us work out a few problems. So consider the first question. Expand 1 by Z square minus 4Z plus 3 in the region 1 less than mod Z less than 3. See, in such regions, we have the Laurent series expansion. That is, you have to express the given function in the form of an infinite series containing positive and negative powers of Z. See, in all 6 questions, first you give its partial fraction. So, you factorize the denominator completely. Then you can see it is 1 by Z minus 3 into Z minus 1. See, this is the factorization of the denominator. So, before doing the partial fraction, you have to factorize the denominator completely. Then you give its partial fraction. See, its partial fraction is A divided by Z minus 3 plus B by Z minus 1. Next, you find the constants A and B by assigning suitable values for z. Before that, you take the LCM on the right side. See, it is z minus 3 into z minus 1. Numerator is a into z minus 1 plus b into z minus 3. Here left side is 1 by z minus 3 into z minus 1. See, here the denominator is common, so you can remove the denominator and you can see 1 is equal to a into z minus 1 plus b into z minus 3. You put z equal to 1. Left side is 1. In the right side, the first term will be 0 when you put z equal to 1. Second term is b into 1 minus 3, that is minus 2. So we have b is equal to minus 1 by 2. Similarly, for getting a, you put z equal to 3. Put z equal to 3. Then 1 equal to 2a plus 0. So a is 1 by 2. So the partial fraction of this term is, there is a shortcut method for finding its partial fraction. Let me illustrate it. Partial fraction of 1 by z minus 3 into z minus 1 is a divided by z minus 3 plus b divided by z minus 1. For getting a, you consider its denominator. See, its denominator is 0 when z equal to 3. See, this is 0 when z equal to 3. You put z equal to 3 here. That is, you put z equal to 3 in the left side except z minus 3. When you put z equal to 3, you can see it is 1 divided by 3 minus 1. That is 1 by 2. That is the value of a. See, already we noticed a is half. Again we got a as half. It's okay. Next, for getting b, you find the value of z whose denominator is 0. Its denominator is 0 if z equal to 1. You put z equal to 1 in the left side except z minus 1. You put z equal to 1 here, then you can see it is 1 by minus 2. That is b value. So we have the partial fraction 1 by z minus 3 by z minus 1 equal to half divided by z minus 3 plus minus half divided by z minus 1. You apply shortcut method and the partial fraction of the given function. So for getting the Laurent series expansion of the given function, now we have to express these two terms in the form of an infinite series by using any one of these suitable results. Result number 1, 1 by 1 plus z is equal to 1 plus z raised to minus 1. That is 1 minus z plus z square minus z cube plus etc. And also we have one more result, 1 by 1 minus z. It can be written as 1 minus z raised to minus 1. And its series expansion is 1 plus z square plus z cube plus etc. And also these two results are applicable only for mod z less than 1. See, its expansion is valid only if modulus of the second term is less than 1. That is mod z less than 1. Also you have to notice that starting term of each term is 1. So for expanding these two terms, you consider the given region. See, the given region is 1 less than mod z less than 3. That is 1 less than mod z and also mod z less than 3. First you express these two regions in the form of less than 1. then it can avoid so many confusions. So this can be written as less than 1 by taking mod z to the left side, that is 1 by mod z less than 1. And here you take 3 to the left side, so you can see mod z by 3 is less than 1. See, these are the two given regions. Say in this region, you have to express these two terms in the form of an infinite series. Here, first term can be written as, you take minus 3 outside. From here, you take minus 3 outside, and you can see it is 1 minus z by 3. See, it is minus 3 plus z, that is z minus 3. See, you can apply this result only if starting term is 1 and modulus of second term is less than 1. Here really you can make it starting term 1 by taking z outside or minus 3 outside. If you take z outside, then z into 1 minus 3 by z. But modulus of 3 by z, mod z by 3 is less than 1. So modulus of 3 by z will be greater than 1. So you can't apply that result. So the convenient way is this one. Again, the second term can be written as minus half divided by. Here you can make the starting term 1 by taking z outside or minus 1 outside. If you take z outside, second term will be 1 by z and its modulus is less than 1. So you have to take z outside. See, here mod z by 3 less than 1, here 1 by mod z less than 1. So you can apply these results. It is minus 1 by 6 into combining the constants, and this can be written as 1 minus z by 3 raised to minus 1 minus 1 by 2 into z, 1 minus 1 by z raised to. While writing 2 and z, you must be very careful. And this is minus 1 by 6 into, and its expansion is 1 plus z by 3 plus z by 3 the whole square plus etc. Minus 1 by 2 z into 1 plus 1 by z plus 1 by z square plus 1 by z cube plus etc. That is minus 1 by 6 into 1 plus z by 3 plus z square by 3 square plus etc. minus 1 by 2 into, you take z inside, 1 by z plus 1 by z square plus 1 by z cube plus etc. See, this is the Laurent series expansion of the given function in the region 1 less than mod z less than 3. Now it's very clear the given function in the form of an infinite series containing positive and negative powers of z. See, it is the combination of two infinite series. The first series is positive powers of z, and the second series is an infinite series containing negative powers of z. That is here z raised to minus 1, its negative power, z raised to minus 2, z raised to minus 3, etc. See, this is the Laurent series expansion of the given function in the given region. See, fortunately in this question, both positive and negative powers of the infinite series are present. Let us work out one more problem. So consider the question. Expand 1 by z square minus 3z plus 2 in the region mod z less than 1. See, in this question, the region is mod z less than 1. See, it's different from the previous question. Let's start. As I mentioned in the previous question, first you have to give the partial fraction of the given function. Here, z square minus 3z plus 2 can be factorized by z z minus 2 into z minus 1. Its partial fraction is a divided by z minus 2 plus b divided by z minus 1. You find the constants a and b by the shortcut method as I mentioned in the previous question. For getting its numerator, you put z equal to 2 here. When z equal to 2, this will be 1. So a is 1. For getting the numerator of z minus 1, you put z equal to 1. You put z equal to 1 here, then you can see 1 divided by minus 1. That is minus 1. So here b is minus 1. See, this is the partial fraction. Next, you have to expand these two terms in the form of an infinite series containing positive and negative powers of z. Sometimes some coefficients may be absent. You can expand these two terms by using these two results suitably. See, you can apply these two results only if modulus of the second term is less than 1 and also the first term is 1. So you have to keep the denominator suitably for applying these results. So for that you consider the given region. The given region is mod z less than 1. See here, you can make the starting term 1 by taking 1 z outside or minus 2 outside. If you take z outside, then the denominator will be 1 minus 2 by z. If 2 by mod z is less than 1, if this is less than 1, then you can return z minus 2 as this one. You check whether its modulus is less than 1 or not. See, the given region is mod z less than 1. If mod z less than 1, then you know its half is also less than 1. That is, mod z by 2 is less than 1. Mod z less than 1. Then what is its half? Mod z by 2. Here mod z less than 1. So mod z by 2 is less than 1. It's very clear. So mod z by 2 is less than 1. But if you write it like this, then 2 by mod z is not less than 1. So you can't write z minus 2 in this way. So that you write the other possibility. You can make the starting term 1 by taking minus 2 outside. So this will be 1 minus z by 2. So here starting term is 1 and modulus of the second term, that is mod z by 2 is less than 1. So it is convenient for applying our second result. See, in all questions, there are two possibilities for making the denominator, making the starting term of the denominator 1. Only one possibility will be suitable. You have to find it. Okay, similarly, here mod z is less. See, our region is mod z is less than 1. So you take minus 1 outside. 1 minus z. So starting term 1 and modulus of the second term is 1. So now it is ready for applying these results, and this equal to minus 1 by 2 into, this can be written as 1 minus z by 2 raised to minus 1 plus 1 minus z raised to minus 1. That is minus half into, its expansion is 1 plus z by 2 plus z by 2 the whole square plus etc. Plus 1 plus z square plus z cube plus etc. That is minus half into 1 plus z by 2 plus z square by 4, that is 2 square plus etc. plus 1 plus z square plus etc. Say this is the infinite series expansion of the given function 1 by z square minus 3z plus 2 in the region mod z equal to 1. That is the required Laurent series expansion. And here Unfortunately, the negative powers of Z is absent. See, this is the required expansion of the given function in the given region, mod Z less than 1.